Hello one and all. Welcome to Tungal online classes. In this session we will discuss concern to magnetic materials. In the last lecture already we have seen that when a material placed in an external magnetic field, that material get magnetized. Already we have seen how the material get magnetized and what are the basic terms concerned to material when the material subjected to external magnetic field. Right. We know that when a material placed in an external magnetic field, that material get magnetized. That material get magnetized either along the direction of applied magnetic field or opposite to direction of applied magnetic field. And when some other material placed in an external magnetic field, those material either they can attract, either they can repel, or either they can strongly attracted by external magnetic field. On that basis, magnetic materials can be classified into three categories. One we are calling diamagnetic material, paramagnetic material and ferromagnetic materials. Actually what it is? When a non-magnet material placed in an external magnetic field, that material get magnetized. The material get magnetized either along direction or opposite to direction or strongly attracted by magnetic field. Right. On that basis, what it is? Magnetic materials can be classified into three categories. One we are calling diamagnetic material, diamagnetic material, diamagnetic materials, diamagnetic materials. Second one is paramagnetic materials, paramagnetic materials, paramagnetic materials, and third one is ferromagnetic materials, ferromagnetic materials. See here, these three types of materials we will study in detail. Before that, we should know about a current loop and magnetic moment and magnetic dipole. See here, every element made up of atoms, and in every atoms electrons are revolving. Due to revolving of electron, there exists a current. Wherever current is exists, there is magnetic field, and wherever magnetic field exists, there is atomic magnet. Wherever atomic magnet exists, there we are calling magnetic dipole moment. That we'll see. See here. Already we know that. Let us see about a current loop, then we will see in detail concern to dia, para and ferromagnetic materials. See here students. We know that this is nothing but atom. This is atom. So inside atom there is a nucleus. This is the nucleus. Consider here electron revolving in clockwise direction. How the electron revolving in this case? Look at me. Electron revolving in clockwise direction like this. Wherever electron revolving clockwise direction, what is the direction of current? The direction of current is the direction to motion opposite to direction of electron. Look at me. I mean, if electrons are revolving in this direction, how the direction of current can exist? Direction of current can exist like this. Wherever current exists, there is magnetic field. Wherever magnetic field, that atom act as a magnetic moment, or the atom is act as a magnetic loop. Look at here. According to right hand rule, if this is nothing but direction of current, this thumb indicates what? Direction of magnetic moment. I mean, if this is nothing but the direction of current in an atom, if we curl our finger, this represent current and thumb represent direction of magnetic moment. Magnetic moment means how it is? Look at me. So if this is nothing but direction of current in this one, then what about this? So this act as a north pole, this act as a north pole, and this one act as a south pole. So that here magnetic moment can develop from where to where? Magnetic moment can develop from south pole to north pole in this direction. Are you following this? But if revolving of electron is in anti-clockwise direction, then how the magnetic moment can exist? Look at me. So again I will take, this is nothing but atom, this is nothing but atom. So this we are calling nucleus. Are you following me? This we are calling nucleus. Now in this case consider electron revolving in electron revolving in anticlockwise direction. If electron revolving in anticlockwise direction, what is the direction of current? This is the direction of current. If this is the direction of current, again the atom is act as a magnetic moment such that this end act as a south, this side act as a north pole, this one act as a north pole, and this one act as a south pole. Then in this case there is magnetic moment from where to where? In this case magnetic moment from where to where? From south pole to north pole. I mean each atom act as a magnetic dipole. Due to that magnetic dipole, magnetic moment had existed. This is one thing, right? And we know that if any material subjected to external magnetic field, that material get magnetized either along the direction of applied magnetic field or opposite to direction of applied magnetic field. There two things are happen. One is when a material subjected to external magnetic field, magnetic dipoles align along the direction of applied magnetic field. Magnetic dipoles are aligned along the direction of applied magnetic field. I mean, see here, if this is nothing but material, this is the material, right? Any material you can take. So I can take this is external magnetic field. I will take this is the external magnetic field. This is the external magnetic field. In this external magnetic field, if any material placed magnetic dipoles, because each atom acts as a magnetic dipole, that magnetic dipole on magnetic dipole torque is acting. Due to that torque, magnetic dipole aligns along the direction of applied magnetic field. I mean, see here, all magnetic moment they can align in this way, in this way, in this way, in this way they aligns. This is one thing. I mean, in external magnetic field, magnetic dipoles aligns along direction of external magnetic field, along direction of external magnetic field, first thing. Second thing is, when any material subjected to external magnetic field, in that material and magnetic moment developed, and so that and magnetic field is induced inside the material directly. When any material subjected to external magnetic field and magnetism is induced in it, that we are calling induced magnetism. See here how it is. Again I will take like this. This is nothing but external magnetic field. I can take this is the external magnetic field. In this way I will take. In this external magnetic field, if any material placed, either it act as a north pole and a south pole. So one end act as a south pole, and what about this one? Second end act as a north pole. So that in this material and magnetic field is induced in it from north pole to south pole outside and south pole to north pole inside, in this direction like this. From north pole to south pole outside the magnet and from south pole to north pole inside the magnet, like this case. Directly, any material subjected to external magnetic field, magnetic moment, so that magnetic field lines are induced in it. Two things are happening. Then let us, I will go directly for what is meant by diamagnetic material. In detail we will see what is diamagnetism, how diamagnetism exists, and what is responsible for diamagnetism and what are their properties. In detail we will see now. Now let us start from diamagnetic materials. Directly, diamagnetism. See here, diamagnetic materials, or you can call it diamagnetism. This concept we will see in detail. Look at me. Concept is diamagnetic materials, or simply I can call it diamagnetism. Diamagnetism. This concept we will see in detail. We will see. See here. In the diamagnetic materials, the net magnetic moment is zero. In diamagnetic materials, net magnetic moment is 0. Initially I can take, see here, first point what I can take in diamagnetic materials, net magnetic moment net magnetic moment is 0. Net magnetic moment is 0. How net magnetic moment is 0, that we'll see. In diamagnetic materials, the outermost orbit contain two pair of electrons. One electron moving in clockwise direction and second electron moving in anti-clockwise direction. So that they contribute a net magnetic moment. That net magnetic moment is 0. So that diamagnetic materials does not a net magnetic moment. I mean directly in diamagnetic materials, no magnetic dipoles are exist. How it is? See here. In diamagnetic materials, electron exists as a pair. I mean outermost orbit contain a pair of electrons. Those pair of electrons, one revolving in clockwise direction and second electron revolving in anti-clockwise direction. How this is? See here. So in diamagnetic materials, lone pair of electrons are there. In lone pair of electrons, one electron revolving in clockwise direction. Due to clockwise direction, how the current exists? This is the direction of the current. Due to current, it exists a magnetic dipole. So that one end acts as a north, second one acts as a south. Here magnetic moment can develop from where to where? Magnetic moment can develop from south pole to north pole. This is one case. But one more also electron revolving. That electron revolving in anti-clockwise direction. How this is? Look at me. Second electron. How second electron can revolving? Separately shall I take? I will take like this. This is same atom I will take. This we are calling nucleus. How electron revolving in this case? Electron revolving like this. Right. If electron revolving in this way, then what about the direction of current? This is the direction of current. Wherever current exists, again it acts as a magnetic dipole. According to right hand rule, now in this case what happens? In this case, this end acts as a south. What about this side? This end acts as a north. Now in this case also magnetic moment develop. How the magnetic moment develop? Magnetic moment can develop from south pole to north pole, like this way. Magnetic moment has developed from south pole to north pole. Look at me. Here lone pair of electrons are exist. One electron revolving in clockwise direction, second one electron revolving in anti-clockwise direction. One electron contribute magnetic moment in upward direction, second electron contribute magnetic moment in downward direction. This magnetic moment are equal and opposite in direction, so that this magnetic moment get cancelled. Wherever magnetic moment get cancelled, then what is net magnetic moment? Net magnetic moment is 0, so that in diamagnetic materials no magnetic dipoles are exist. No magnetic dipoles are exist. In diamagnetic materials. But one thing I said that any material subjected to external magnetic field, it get magnetized. I mean magnetic field lines are inducing it. That we'll see. When this diamagnetic material subjected to external magnetic field, it contributes the magnetization. That magnetization always opposite to direction of magnetic field, because reason is there. Reason is one electron moving in clockwise direction, second electron moving in anti-clockwise direction, they contribute net magnetic moment on application of external magnetic field, so that it is slightly magnetized opposite to direction of magnetic field. How it is? Look at me. Now simply I will take a diamagnetic material slab. I will take, say, diamagnetic material. I can take the H2, I can take the N2 slab, or you can take gold, you can take silver, right? You can take diamond. All these are nothing but diamagnetic materials. Look at here. To this diamagnetic slab, I want to apply external magnetic field. Simply, how to apply external magnetic field? If I apply external magnetic field, this is nothing but external magnetic field I want to apply. This is the external magnetic field. Are you following? This magnetic field what value? It is nothing but P value. Here in diamagnetic material, lone pair of electrons are there. Those lone pair of electrons contribute to slightly magnetization, but that magnetization always opposite to direction of magnetic field. I mean, when this slab subjected to this external magnetic field, slightly magnetic dipoles are induced and the magnetic dipoles are slightly opposite to direction of applied magnetic field. Applied magnetic field. I mean, this material gets slightly magnetized opposite to direction of magnetic field. So that here new magnetic field lines are induced, that new magnetic field lines are always opposite to external magnetic field, so that this diamagnetic materials weakly repelled by external magnetic field. Why they are weakly repelled by magnetic field? When they subjected to external magnetic field, they get slightly magnetized opposite to direction of magnetic field. I mean, in this way, net magnetic moment developed. This net magnetic moment developed always opposite to direction of applied magnetic field. See here, this we are calling net magnetic moment. This net magnetization always opposite to direction of magnetic field. Not all. So slight magnetic dipoles are developed in it. Those are always opposite to direction of magnetic field. I can call the materials which are weakly repelled by external magnetic field, those I can call a diamagnetic materials, because when they subjected to external magnetic field, it get magnetized, slightly magnetized opposite to direction of applied magnetic field. Right? Then how to define diamagnetic materials? The materials which are weakly repelled by magnetic field, those are we are calling diamagnetic materials. Here, how to say the definition? Definition of diamagnetic materials: the materials which are weakly repelled, materials which are weakly repelled, weakly repelled by external magnetic field, those are called as the diamagnetic materials. See here, for example, you can take gold, you can take silver, you can take N2, you can take H2, all these are nothing but examples for diamagnetic material. In this diamagnetic material, the net magnetic moment developed, that net magnetic moment always opposite to direction of applied magnetic field. Now, let us see what are few properties of diamagnetic material in detail. We will see that's here. Next concept is property of diamagnetic materials. Properties of diamagnetic materials. Let us see one by one. What are few properties of the diamagnetic materials? In detail we will see. See here. Concept is properties of diamagnetic materials. Properties of diamagnetic materials. Properties of diamagnetic materials. One by one see what are the properties of the diamagnetic materials. Let us take first property. The first property of the magnetic field is there is no magnetic dipoles or exist in diamagnetic materials. What is that? No magnetic dipoles. No magnetic dipoles. No magnetic dipoles. Dipoles exist. No magnetic dipoles or exist. This is first property. Second property you can call, when diamagnetic materials subjected to external magnetic field, they get weakly magnetized opposite to direction of magnetic field. Due to that weakly magnetized, they repel by external magnetic field. How this is? Second property, diamagnetic materials are weakly repelled by external magnetic field. These are weakly repelled by. These are weakly repelled by. Repelled by external magnetic field. External magnetic field. External magnetic field. This is second property. But when this diamagnetic material is subjected to external magnetic field, no magnetic lines of forces are passes through it. Almost all magnetic field lines are repelled by these magnetic materials. How the situation it is? Look at me. Simply I will take, look at me. Now we are going to discuss what is magnetic permeability of the diamagnetic materials. Magnetic permeability means the ability of the magnetic material to allow passes magnetic field lines to pass through it. I mean, ability of the material to allow magnetic field lines to pass through it, that ability we are calling magnetic permeability. When diamagnetic material placed in external magnetic field, almost all the magnetic field lines are repelled by it. Situation like this. See here. Simply shall I take? I can take like this. This is nothing but one diamagnetic slab. Either can take gold, silver or diamond, or can take H2N2 like this slab. When magnetic field lines are entered, let us take, I want to apply external magnetic field. Whenever external magnetic field goes, they repel like this. Whenever external magnetic field goes, they repel like this. Or few lines only passes like this. This is the situation. How the situation occurs? When diamagnetic material subject to external magnetic field, almost all the magnetic field lines are repelled. Due to that, magnetic permeability of the diamagnetic material is very, very small. Magnetic permeability of the diamagnetic material is very, very small because no magnetic lines of forces are passes through it. We know that magnetic permeability can be represented by mu. So what is mu? Mu is equal to what value? Mu naught plus mu r. This value is very, very small. If this is very, very small, then what about this? This also very, very small. I mean, the magnetic permeability or relative permeability, it is always less than 1. Less than 1 mean either you can take -2, you can take -3 like this. Less than 1. Less than 1 mean directly it is less than 0. Less than 1 mean -1, -2, minus like this. No magnetic lines of force or passes. Mu r is what value? Mu r is always greater than what value? Less than 1 or greater than 0 and less than 1. Look at me. This mu r is always not mu r. Less than 1 mean what value? This value either can take 0.5, you can take. So what you can take? You can take 0.6. Either you can take what value? 0.7 you can take. Mu r is very, very smaller. Magnetic permeability is very, very smaller. I mean, if you passes 100 magnetic field lines through diamagnetic materials, out of 100 only 1-2 magnetic field lines are passes through it. Right around. Then if mu r is very, very smaller, what you are taking is third property? No almost all magnetic field lines are repelled by diamagnetic materials. If mu r is this value, I mean magnetization always opposite. If magnetization always opposite, then mu r equal to this value, either very, very smaller value. If this is very, very smaller value, then what about the fourth property? What is magnetic susceptibility of the diamagnetic materials? See here. We know that this relation indicates what? Xi I is equal to xi m is equal to what value? Mu r is equal to what value? So mu r is equal to 1 plus xi m. 1 plus xi m, or what is xi m from this? Xi m, magnetic susceptibility. What value it is? It is nothing but mu r minus 1. Are you following? Mu r magnetic permeability of order this value, of order this value. So that what it indicates? look at me, if this is this, for example, I can take this value. So mu r is equal to what value? Xi m. Xi m is equal to mu r. Mu r is how much I am taking? For example, I am taking 0.5 I am taking. So what about this value? -1. Then what are Xi m value? Xi m value what value? This is minus always. I mean, magnetic susceptibility of the diamagnetic material is very low and it becomes always negative. From this you can take one more confirmation. See here, this magnetization is equal to what value? So this is nothing but I is equal to, magnetization, Xi m is equal to what value? Xi m is equal to what value? I divided by H. I divided by H, right? This relation already we know. Or I is equal to what value? From this, I is equal to Xi m into what value? H value. Right? We know that when diamagnetic material placed in external magnetic field, it magnetized, but it slightly magnetized opposite. Opposite means this value is negative. If this is negative, then what about this value? This also negative. So Xi m is negative. I mean, what is the fourth property? Magnetic susceptibility of the diamagnetic material is low and it becomes negative. This is fourth property. A fifth property I can call. Let us take what about the fifth property? See here. Fifth property I can call. Fifth property is when a diamagnetic material placed in a non-uniform magnetic field. When it is placed in non-uniform magnetic field, it moves from stronger region to weaker region. Because one reason is that diamagnetic materials are weakly repelled by external magnetic field. Repel means it move from where to where? It move from stronger region to weaker region. Look at me here. So what is fifth property? When diamagnetic material placed in non-uniform magnetic field, diamagnetic materials moves from stronger region to weaker region, stronger to weaker regions, See here, because the reason is that how non-uniform magnetic field can be represented. Look at me. So this I can call non-uniform magnetic field lines. Are you following? So this we are calling non-uniform magnetic field lines. I can call non-uniform magnetic field lines. In this non-uniform magnetic field, just I want to place a diamagnetic material. How it moves? It moves from stronger region to weaker region because they can repel. Why they can repel? They get magnetized opposite to direction of external magnetic field. And this is one case. Second case, the magnetization of the diamagnetic material independent on temperature. No matter how much a temperature increase, when it is subjected to external magnetic field, its magnetization never effect. Simply, it is slightly magnetized opposite to direction of magnetic field. Directly we can call magnetic susceptibility of the diamagnetic material. It is independent on temperature. See here. Next property what I can call? Shall I take one more property here? Sixth property I can call magnetic susceptibility. Magnetic susceptibility means Xi m. Magnetic susceptibility of diamagnetic materials. Diamagnetic materials independent on temperature. I mean, its magnetization property, it is not depends on temperature. But one more is there. Already we know that when diamagnetic material subjected to external magnetic field, all magnetic field lines are repelled by it. If the case, no magnetic field lines are passes through diamagnetic material, those materials are called as superconductor. Those are called as superconductor. If the material exhibits perfectly superconductor, then that phenomena we are calling Meissner effect. Superconductor means the material which does not allow to pass magnetic field lines to pass through it. Those we are calling superconductors. Because one of the property of the magnetic field lines can pass through conductors, insulators, but they never passes superconductor. Superconductor means the material which maintain at zero temperature, that we are calling superconductors. In superconductors, never magnetic field lines are passes. If perfect no magnetic field lines are passes through material, that effect we are calling Meissner effect. Meissner effect means the perfect diamagnetism. Perfect diamagnetism means all magnetic field lines can repel by external magnetic field when a material subjected to external magnetic field. Look at here. I mean, if no magnetic field lines passes through material, that effect we are calling Meissner effect, and Meissner effect only exists in superconductors. See here. Simply I can call the one more phenomena here, the perfect diamagnetism. Perfect diamagnetism. Perfect diamagnetism. Diamagnetism. Perfect diamagnetism is called as Meissner effect. Meissner effect. This property. Simply, what are the properties of the diamagnetic material? No magnetic dipoles are exist in diamagnetic material. These are weakly repelled by magnetic field. Almost all magnetic field lines are never passed through material. I mean, magnetic permeability is very smaller, so that magnetic susceptibility is a negative value. When diamagnetic material subjected to external magnetic field, they move from stronger region to weaker region. Second one is that magnetic susceptibility or magnetization of the diamagnetic material independent on temperature. And the phenomena where no magnetic field lines are passed through material, that phenomena we are calling Meissner effect, and Meissner effect only possible in superconductors. These are concerned to diamagnetic materials. Now let us go what is meant by paramagnetic materials, how paramagnetic material phenomena can be exist, that we will see. See here. Next one is paramagnetic materials. Paramagnetic materials. Concept is the paramagnetic materials. Look at me. Paramagnetic materials. Let us initially how paramagnetism exists and what are the properties of the paramagnetic materials, students. In some materials, the outermost orbit contain unpaired electrons. Due to that unpaired electrons, it contributes a net magnetic moment. Because in diamagnetic materials, there what is exist? Always outermost orbit contain the lone pair of electrons. One electron revolving in clockwise direction, second electron revolving in anti-clockwise direction, so that one magnetic moment in one direction, second magnetic moment in another direction, right? But in some other material, the outermost orbit contain the unpaired electrons. The unpaired electrons contribute magnetic moment. I mean, each atom contribute magnetic moment. Due to that magnetic moment, in some other materials, always exist a permanent magnetic dipole. They exist permanent magnetic dipole. So I will take a sodium slab. In the sodium slab, how one atom contribute magnetic moment, that we'll see. Look at here. See here. I can take this nothing but the sodium slab I can take. So sodium is nothing but a paramagnetic materials. It is a paramagnetic material. In this sodium slab, just only I want to take and one atom how it contribute magnetic dipole and how it contribute magnetic moment. That we'll see. See here, we know that the sodium contain how much it has atomic number. Atomic number is nothing but L1. So shall I write electronic configuration of the sodium? How to write? So electronic configuration is nothing but what value? So 1s2, 2s2, what about this? 2p6, what about this? 3s1. Right around. So 2 plus 2 4, 4 plus 6 10, 10 plus 1, that is L1. Right around. How electrons are exist? Look at me. Electron can exist always like this. So 1 was 1, it contains lone pair of electrons. One electron in upward direction, second one is like this. Second one, what about second one? Second one also like this. 1s1, 2s2. Then what about this? The second egg. So one electron in upward, second one like this, again upward, downward, second one upward and downward like this. Are you following me? Then finally 3s1, this always unpaired electron. This unpaired electron always contribute magnetic moment. It always contribute magnetic moment. Due to magnetic moment in paramagnetic material, they always has permanent magnetic moment. Let us take one magnetic moment. How it orient? One magnetic moment always orient like this. For second atom, how the magnetic moment can exist? Like this. Third one, how they exist? Like this. Fourth one, they exist like this. Like this way. So each atom contribute magnetic moment, and that magnetic moment always orient in a different direction. Always orient in different direction. I mean, each atom contribute magnetic moment. Each atom contribute magnetic moment due to unpaired electron, and that magnetic moment orient randomly in all possible direction in absence of external magnetic field. I mean, in absence of external magnetic field, the paramagnetic material has a permanent dipole moment. They exist permanent dipole moment. This is what case? This is in absence of external magnetic field. In absence of external magnetic field. Absence of external magnetic field. In absence of external magnetic field, each atom contribute magnetic dipole moment. This magnetic dipole moment orient randomly in all possible direction, and net magnetic moment is 0. Actually, they have permanent dipole moment, but one dipole moment acting in one direction, another acting in another direction, one acting in downward, second acting in upward. The net magnetic moment, I'm asking only one atom, I am asking about all atom. For all atom in absence of external magnetic field, net magnetic moment is 0. Net magnetic moment is 0 overall all. But every atom acts as a permanent dipole moment. Every atom acts as a, overall I am saying, overall it is 0. Why it is 0? One magnetic moment acting in upward, second one downward, one acting in forward direction, in backward direction. So that net magnetic moment must be 0. But whenever external magnetic field is applied to a paramagnetic materials, wherever external magnetic field is applied, one thing already said that whenever any material is subjected to external magnetic field, magnetic dipoles align along the direction of applied magnetic field. Look at me. Now I want to apply external magnetic field to this. Then what happens? See here. Shall I take? Now I will take a paramagnetic slab. So let us take sodium. We can take chromium. You can take antimony. So these are nothing but examples for paramagnetic materials. In this paramagnetic materials, just I want to apply external magnetic field. Look at me. This is external magnetic field I want to apply. Look at the situation. Simply, this is nothing but external magnetic field. External magnetic field just I want to apply. External magnetic field. Wherever external magnetic field is applied, This magnetic dipoles try to align along the direction of applied magnetic field. They try to align, each dipoles try to align along the direction of applied magnetic field. How it is? Look at me. In this external magnetic field, all these magnetic dipoles, how they align? They align partially along the direction of applied magnetic field. I mean, this material get magnetized. This material get magnetized slightly along the direction of applied magnetic field. Then look at me. How to take here? In presence of this magnetic field, all the magnetic dipoles, they aligns like this. Some of the magnetic dipoles are there in this way, in this way, in this way, in this way, like this, like this. How they get magnetized? They magnetized along the direction of magnetic field, and this magnetization not exactly along the direction of applied magnetic field. Simply they try to align along the direction of applied magnetic field. I mean, this material get magnetized along the direction of applied magnetic field. How they magnetize? They magnetized along the direction of applied magnetic field. If they magnetized along the direction of applied magnetic field, then this material weakly attracted by magnetic field. They get magnetized. They get magnetized along the direction of applied magnetic field. Due to that fact only, the paramagnetic materials which are weakly attracted by external magnetic field. From this I can define what is paramagnetic material. Here what is paramagnetic material? The materials which are weakly attracted by magnetic field, that material is called as paramagnetic material. Look at it. The materials which are weakly attracted, the materials which are weakly attracted, the materials which are weakly attracted, which are weakly attracted, weakly attracted, weakly attracted by external magnetic field, external magnetic field. So those are called as paramagnetic material. I mean, the materials in which there is permanent magnetic moment or permanent magnetic dipoles, those are also called as paramagnetic materials. But whenever this magnetic field is removed, external magnetic field is removed, this magnetization becomes vanish. Magnetization becomes vanish. Vanish means, again, like the situation is there in presence of this external magnetic field. Whenever this magnetic field is removed, again the situation becomes like this. Right? Then what are the properties of the paramagnetic material? That we'll see in detail. Now let us see what are the properties of paramagnetic materials. See here. Second thing is properties of paramagnetic materials. Look at it. Concept is properties of paramagnetic materials. Properties of paramagnetic materials. See here. First property, in paramagnetic materials always exist magnetic dipoles. See here, the material which exist magnetic dipoles, they exist permanent magnetic dipoles. Permanent they exist magnetic dipoles, simply they exist magnetic dipoles, exist magnetic dipoles. First property. Second property, paramagnetic materials magnetized, slightly magnetized along the direction of applied magnetic field, hence the attract. Due to attraction, how to write the property? Paramagnetic materials are weakly attracted by external magnetic field. Paramagnetic materials weakly attracted by external magnetic field. Second property. See here. Third property, let us take what is magnetic permeability. When paramagnetic material subjected external magnetic field, almost all magnetic field lines can passes. I mean, its magnetic permeability is greater than 1. Magnetic permeability is always greater than 1, but not more. Look at me. So I can take third property. Look at me. I will take a paramagnetic material. Say I can take chromium. You can take sodium. You can take antimony. Right? When it is subjected to external, say let us take it is nothing but sodium. I will take it. Right? When it is placed in external magnetic field, almost all magnetic field lines can passes. Almost all, like this. So that its magnetic permeability is slightly greater than 1. Look at me. I mean, it get magnetized along the direction of applied magnetic field, like this. Right or wrong? So that how it is, already we know that's the relation. So Xm is equal to what value? Xm is equal to I divided by H. I mean, it get magnetized along the direction of applied magnetic field. This magnetization, it is slightly more. I mean, it is greater than 1. I mean, ability of this material to allow magnetic field lines to pass through is more. Its magnetic permeability always greater than 1. Then what is magnetic susceptibility? That we'll see. See here. Look at me. This value already we know that. So mu r is equal to what? Xm is equal to what value? So Xm is equal to mu r is equal to 1 plus Xm. Mu r is equal to 1 plus Im, right or wrong? Its magnetic permeability is always more. More mean, so it is of the order 1.5, of the order 1.7, of the order 1.8, like this. But not greater than 2, greater than 1, but not greater than 2. Look at it. How it is lying? See here. This magnetic permeability, ability of the magnetic field lines to allow, how it is passes? Either it may be 1.5, either it is 1.8, either it is 1.6, like this. I mean, greater than 1 and less than 2. Magnetic permeability of the paramagnetic materials. If mu r is this value, then what about this magnetic susceptibility? Look at me. Shall I take only one example for this? For example, I can take Xm is equal to what value? Xm is equal to mu r minus 1. Xm is equal to mu r minus 1. So again, Xm is equal to what value? Mu r, how much I am taking? For example, I can taking 1.6 minus 1 is equal to what value? 0.6. Then from this what you can confirm? Magnetic permeability is more and magnetic susceptibility is always positive but less than 1. See here. Magnetic permeability of the paramagnetic material is more and magnetic susceptibility. Shall I take fourth property? Magnetic susceptibility of the paramagnetic material is always positive. And must be less than 1. This is one property. But when paramagnetic material placed in a non-uniform magnetic field, how they can move? As in case of diamagnetic material, what you have seen? When a paramagnetic material placed in a non-uniform magnetic field, how they move? They move from stronger region to weaker region because they was repel. They was repel. In this case, what happened? They attract, weakly attract. Weakly attract mean when a paramagnetic material is subjected to external magnetic field, they move from weaker region to stronger region because of attraction. So, next property I can call. When diamagnetic material plays the external magnetic field, they moves from weaker region to stronger region, in non-uniform magnetic field. Non-uniform magnetic field like this. Then what is magnetization? Already I said that when external magnetic field is removed, again all magnetic dipoles are tried to align randomly in all possible directions so that net magnetic moment is zero. I mean, magnetic susceptibility or magnetization of paramagnetic material depends on temperature. Because when external magnetic field is applied, they try to align along the direction of applied magnetic field. When external field is removed, again they try to align randomly in all possible direction. On that basis, magnetization and magnetic susceptibilities depends on temperature. See here, next property I can call. The magnetization of paramagnetic materials depends on temperature. So these are the few property of the paramagnetic materials, right? Then later we'll discuss how magnetization depends on temperature. Magnetization of paramagnetic material depends on temperature. That we'll see in detail, right? Look at me. Next concept is Curie Law of Paramagnetism. That concept we'll see. Curie Law of Paramagnetism concept. See here. Concept is Curie Law. Curie's Law of Paramagnetism. See here. This we'll see in detail. Look at me. Students, now I will take external magnetic field. In external magnetic field, if a paramagnetic slab is placed. See here. I will take a paramagnetic slab. This is the paramagnetic slab, right? In this paramagnetic slab, just I want to apply external magnetic field. Right or wrong? This external magnetic field just I want to replace by B, right? When external magnetic field is increased gradually, this paramagnetic material gradually magnetized along the direction of applied magnetic field. I mean, magnetization of this paramagnetic material that directly depends on external magnetic field. How it is? See here. It get magnetized along the direction of applied magnetic field. It depends on external magnetic field. How to say? Magnetization of the paramagnetic material directly proportional to external magnetic field. It is going to be only on experimentally. And inversely proportional to temperature. Magnetization, how much temperature decrease, and how much external magnetic field increase, that much this magnetic material get magnetized. And point of tagligada e material hang magnetize ಆಗ್ತದ hang magnetic moment develop ಆಗ್ತದ ಈ magnetic moment develop ಆಗೋದು external magnetic field ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗ್ತದ ಎಷ್ಟು magnetic field increase ಮಾಡ್ತೀರಿ ಅಷ್ಟೇ magnetic moment develop ಆಗ್ತದ ಎಷ್ಟು ಟೆಂಪರೇಚರ್ ನ ಡಿಕ್ರೀಸ್ ಮಾಡ್ತೀರಿ ಅಷ್ಟು magnetic moment ಏನಾಗ್ತದ ಡೆವಲಪ್ ಆಗ್ತದ simply magnetization of the paramagnetic material directly proportional to external magnetic field and inversely proportional to absolute temperature, or else magnetization of the paramagnetic material equal to constant constant C B divided by T, where C is constant, this constant is called as Curie constant. What is C here? C is equal to what value? C is equal to Curie constant. Right? Then we know that external magnetic field, this external magnetic field is equal to what value? B is equal to mu into H, where B is nothing but magnetic induction and H is what? Magnetic intensity, magnetizing intensity. Right? Then let us fill this relation here. I is equal to what? I is equal to C kept up same. So B is equal to mu into H whole divided by what value? T. Right or wrong? Again, see here. H bring this side. I divided by H is equal to what value? Is equal to C mu divided by what value? T. I by H is equal to what value? Psi m. So constant C into mu divided by T. C is constant, mu also constant, magnetic permeability. Are you following? Then from this again, okay, from this what can take the Curie law of paramagnetism? Magnetic susceptibility of the paramagnetic material inversely proportional to absolute temperature. This is Curie law of paramagnetism. Right? Later we will see one more type of material that we are calling ferromagnetic materials. Ferromagnetic materials in detail we will see. See here. Next one is ferromagnetic materials. Ferromagnetic materials. See here. Actually, the ferromagnetic materials, these are special case of paramagnetic materials. Here difference is, in paramagnetic materials, magnetic dipoles are randomly oriented. But in ferromagnetic materials, all magnetic dipoles are arranged in a small region such that all magnetic dipoles have same direction. See here, how the situation of the ferromagnetic materials actually. I can take the ferromagnetic materials, say iron, nickel, cobalt, all these are nothing but examples for ferromagnetic materials. In this ferromagnetic materials, magnetic dipoles are oriented in a small given region. All magnetic dipoles aligns in a definite direction. How they exist? So I can divide this material into 4 regions. In some other region, magnetic dipoles are exist like this. So in some other regions, magnetic dipoles are exist like this. In some other regions, magnetic dipoles are exist like this. In some other region, magnetic dipoles are exist like this. Like this magnetic dipoles are exist. See here. I mean, in a given small region, all magnetic dipoles has same direction. This small region is called as domains. What can call domains? Domains is a smaller region where all magnetic moment has same direction. I can call this is domain, this is domain, this is domain, this is domain. This domain is of the order 1 millimeter. In one domain, minimum how many atoms are there? 10⁸ atoms are there. Right? But this is only in absence of external magnetic field. When external magnetic field is applied, all domains align along the direction of applied magnetic field. So how it actually happens? When external magnetic field is applied, how the domains can there actually? This second call external magnetic field. Right or wrong? This one I can call external magnetic field. When external magnetic field is applied, all the domains, whatever these domains, they try to align, perfectly aligns along the direction of applied magnetic field. They perfectly aligns. Perfectly aligns. I mean, they perfectly aligns mean they get strongly magnetized along the direction of applied magnetic field. How they strongly magnetized? They strongly magnetized along the direction of applied magnetic field. Hence that the ferromagnetic material which are strongly attracted by magnetic field, or the material which strongly attracted by magnetic field, those materials are called as ferromagnetic materials. See here. But whenever temperature of the ferromagnetic material gradually increase, then magnetization property going to be losses at a particular temperature. At a particular temperature, the ferromagnetic material act as a paramagnetic materials. And remember, they get strongly magnetized along the direction of applied magnetic field. One case. Second one is, when ferromagnetic material is subjected to external magnetic field lines are crowded in it. I mean, almost all magnetic field lines are passed through it. See here. How it is? Look at me. So I can take, it is a ferromagnetic material, say iron I can take, this is iron, or nickel you can take. This ferromagnetic material, if it is subjected to external magnetic field, all magnetic field lines are passes. Almost all magnetic field lines are passes. Are you following me? Right? I mean, magnetic field lines are crowded in it. Remember this. I mean, it has high magnetic permeability. It has a high magnetic permeability. By taking this, let us see what are the properties of ferromagnetic materials in detail. See here. Look at me. See here. Next one is properties of ferromagnetic materials. Properties of ferromagnetic materials. Properties of ferromagnetic materials. Right? First property. Ferromagnetic materials are strongly attracted by magnetic field. See here. They strongly attracted by magnetic field. Strongly attracts by external magnetic field. External magnetic field, not EMF. External magnetic field. Right? Next one. When ferromagnetic material placed in a non-uniform magnetic field, they move from stronger region to weaker region. They move from weaker region to stronger region due to attraction. And when ferromagnetic material is subjected to external magnetic field, shall I take this external magnetic field? All magnetic field lines are passes. All magnetic field lines are passes. So that magnetic permeability of ferromagnetic material is very high and greater than 1. Greater than 1, like 2, 3, 4, 5, 6, like this you can take. I mean, it has high magnetic permeability. Magnetic permeability is more. Then let us take what about magnetic susceptibility from this relation. What is magnetic susceptibility relation? So mu r is equal to what value? 1 plus psi m. So mu r is of the order. Mu r is equal to either 2, 3, 4, 100, like this you can take, or 1000 you can take, because more magnetic field lines are passes. Right on this. Then look at me here. We can take from this psi m is equal to what value? Mu r minus 1. Mu r is equal to what value? Either 2, 3, 4. So I will take 3 value. It is 1. Then what is mu r? Mu r is always positive and greater than 1. Greater than 1. And also, when temperature of the ferromagnetic material can increase, it convert into paramagnetic material. At a particular temperature, when temperature increase at a particular temperature, the ferromagnetic material act as a paramagnetic material. So at a particular temperature, when ferromagnetic material converted to paramagnetic material, that temperature is called as Curie temperature. At this temperature, what happened? At this temperature, ferromagnetic material is converted into ferromagnetic material is converted into paramagnetic material, because magnetization of the ferromagnetic material depends on temperature. As temperature increase gradually, the ferromagnetic material converted into paramagnetic material. So that fourth property I can call, or fifth property I can call, see here, magnetization of ferromagnetic material depends on temperature. Right? So these are a few properties of para, dia and ferromagnetic materials. Remaining concept we will see in the next class. Thank you guys.